Assalamu alaikum. Physical Geology, Chapter 8, Metamorphic Rocks. Presented by Khalid Lamrouni, PhD in Geology from Texas A&M University. And Khalid Lamrouni is a staff member at the Department of Earth Sciences, Yunus University, Benghazi, Barga State, Cyrenaica State. And the reference used in this for these lectures is Essentials of Geology. This is the Department of Earth Sciences at Yunus University, and this is the main entrance of Yunus University. This is the Prince of Barga State, Cyrenaica State, Idris Sunusi, and the founder of Yunus University. Here's the flag of Barga State behind Prince Idris, and this is the capital of Barga State, Benghazi City. This is the chief commander of the Sunusi Army, Omar al-Mukhtar. And this is the flag of, the map of Barga State or Cyrenaica State. The outlines of the Metamorphic Rocks lecture: Metamorphism, 3 settings of metamorphism during mountain building, contact metamorphism along fault zones, agents of metamorphism, heating, pressure, and chemically active fluids, textural and mineralogical changes, foliation and non-foliation, what drives metamorphism, parent rocks and metamorphic grade, metamorphic textures, occurrence of metamorphic rocks, metamorphic environments, metamorphic zones, and index minerals. So let's go with the metamorphic rocks. Metamorphism. What's metamorphism? The transformation of pre-existing rock. So the rock is already there. This rock, or the parent rock that will change and metamorphose, can be either sedimentary, metamorphic, or igneous. And there are agents for metamorphism: heat, pressure, and chemically active fluids. And what changes that will happen? Textural as well as mineralogical. The main point here for metamorphism: the rock must remain solid. The rock that change it or transform it into metamorphic rock must remain solid. If we pass it, if melting happened, that means we passed the metamorphism region or field of metamorphism, and then we'll go to the igneous rock and and magma field. But for metamorphism, to say this rock is a metamorphic rock, must remain solid during the transformation. 3 settings of metamorphism during mountain building, and this it's mainly pressure. Great quantities of rocks are subjected to the intense stress and temperature associated with larger scale deformation, called regional metamorphism. So regional metamorphism, we have pressure and temperature. Contact metamorphism, rocks in contact or close proximity to a massive magma. So the main factor here, the main agent, is temperature for contact metamorphism. Along fault zones, here rocks broken or distorted as crustal blocks on opposite sides of a fault grind past one another. And that will generate a lot of heat, pressure, and temperature. And then metamorphism will happen. Agents of metamorphism: heat, pressure, chemically active fluids. Heat as an agent of metamorphism. Rocks formed near the Earth's surface may subject to intense heat when they are introduced by molten material rising from below. Okay, when we have magma rising from below, when it comes close to the surface, will cause metamorphism and deform the rocks close to the surface, change their chemistry and their mineralogical composition, and sometimes their texture. Here they said the Earth's material are continually being transported to great depths at convergent plate boundaries. So at convergent plate boundaries, subduction zones, we have metamorphism too. Both here we have heat. Pressure as a metamorphic agent. Buried rocks are subject to pressure exerted by the load of material above. This is one. So when we have sediments buried and the sediment's thickness or the package of sedimentary rocks are so thick, packages of sedimentary rocks are so thick, that will cause a lot of pressure at the lower packages and lead to metamorphism. And the other place where we have pressure is main factor of metamorphism, mountain buildings. Here there's a note, shear stress occurs to the rocks exist near surface during the formation. So any rocks near the surface will have shear metamorphism, shear stress, sorry. Chemically active fluids. Chemically active fluids also enhance the metamorphism process along the oceanic ridges, the divergent boundaries. You're talking about the divergent boundaries. Along oceanic ridge systems, seawater circulation through the still hot rocks helps transform dark basaltic into metamorphic minerals such as serpentine and talc. So at the mid-oceanic ridges, the magma coming from the bottom, very hot, and the seawater is cold, and the circulation between hot and cold that will transform basaltic rock into metamorphic rocks, serpentine, and talc. Textural and mineralogical changes. Here, the degree of metamorphism is reflected in the textural and mineralogy of a metamorphic rock. So, as you change, as the grade of metamorphism changes, the texture will give us different textures and different mineralogical composition. What happens? Under the pressure of metamorphism, some mineral grains become oriented and aligned at right angles to the pressure, correct? So we have alignment and reorientation of the grains, the mineral grains inside the rock. And this orientation, what will lead to the mineral grains orientation, will give us the foliation or the foliated texture. Types of foliations are depending to a large extent upon the degree of metamorphism, correct? The rocks of a platy or scaly appearance is called schistose, and the rock names schist. And schists, as you know, they are named based on their mineral constituents. Sometimes mica schist, muscovite schist. But on the other side, we have non-foliated rocks. Not all metamorphic rocks have foliated texture, like fine-grained limestones, metamorphosed into marble. Limestone metamorphosed into marble. Quartz metamorphosed into quartzite. So in summary, metamorphic process cause many changes in rocks, including what changes metamorphism can do to the rock. Increase the density of the rock. Increased growth of larger crystals. Crystals will be larger inside. Reorientation of mineral grains into a layered or banded appearance known as foliation. 4. Transformation of low temperature minerals into high temperature minerals. 6. The introduction of ions generates new minerals. So these 5 changes will happen. So what drives metamorphism? Heat, pressure, chemically active fluids. Now let's go through details. Heat, most important agent. Recrystallization is the process of forming new, stable minerals larger than the original. Okay, so we'll get the process of recrystallization, and that will lead to formation of larger and more stable minerals with larger crystals. Two sources of heat. We have two sources of heat: geothermal gradient and contact metamorphism. What's the geothermal gradient? An increase in temperature with depth. As you go deeper, digging deeper inside the earth, for 1 kilometer, there is an increase in temperature of 25 degrees Celsius. Contact metamorphism, rising mantle plumes. Mantle plumes, when they rise and touch the Earth's material or crust, that will create, that's a contact metamorphism. Will create metamorphic zone or halo of metamorphic rocks. Pressure, we have confining pressure, differential pressure, and compressional stress. Confining pressure, force applied, or forces are applied equally in all directions. The example to water pressure, or analogs to water pressure. What confining pressure causes? It causes the spaces between mineral grains to become closer, so the rock will be more tight. Differential stress is different. Forces are unequal in different directions. Stresses are greater in one direction. Compressional stress, rocks are squeezed as if in a vice, shortened in one direction and elongated in the other direction. So still compressional is still differential stress. Now chemically active fluids enhance migration of ions, aids in recrystallization of existing minerals. In some environments, fluids can transport mineral matter over considerable distances. Okay. The importance of parent rock. The parent rock, the original rock before the metamorphism process. Okay, most metamorphic rocks have the same overall chemical composition as the original parent rock. And mineral makeup determines the degree to which each metamorphic agent will cause change. So let's look at the pressure. This is the confining pressure and differential pressure. Confining pressure, for example, when we have sediments in the sedimentary basin, in the load of the sediments or the upper packages on the lower packages, what's what we call a confining pressure. It's equal from all sides. And that will cause decrease in that size, in the package size. So the package was of this size and now decreased to this size because the confining pressure can decrease the volume. On the other side, the differential stress will have, this is the original package, and if you have stress or forces from two sides larger than the other sides, deformation will happen. As the case in the mountain buildings. So this is confining pressure, decrease the size without deformation, but the differential stress or pressure will cause deformation. Parent rocks and metamorphic grades. Every metamorphic rock has a parent rock. The rock, what's the parent rock? The rock from which it formed. Parent rocks can be igneous, sedimentary, or other metamorphic rocks. Okay, so any metamorphic rock is parents, or its parent can be sedimentary, igneous, or metamorphic. Now, metamorphic grade. What's the metamorphic grade definition? Is the degree to which the parent rock changes during metamorphism. And we have a progress from low grade, low temperature, low pressure, to high grade of metamorphism, which is high temperature, high pressure. Note, during metamorphism, the rock must remain solid, no melting. Okay, parent rock of metamorphic grades. The parent rock here is shale, and the product is slate. happened here, the clay minerals, they were random, packed loosely, but when they were subjected to pressure, they got aligned and packed. This is what we call it slate, and the parent of the slate is shale. The difference between shale and slate, you will see the breaking zones or cleavage of the shale is perpendicular to the bedding plane. It's up the opposite of the shale. The shale can be split along the bedding planes, but the slate along or perpendicular can be split perpendicular to the bedding planes. Here we have gneiss. You see this rock is called gneiss, has bands, white, dark, white felsic, dark mafic. What happened? The parent was a granodiorite, igneous rock. The crystals were randomly arranged, but when subject to pressure, the crystals aligned in along zones. The white ones felsic, feldspar and silica, and the dark bands is mafic, iron and magnesium. Metamorphic texture. Texture, what texture? Describes the size, shape, and arrangement of mineral grains. That's the texture. Describes three things: size, shape, and arrangement of mineral grains. So metamorphic rocks can display preferred orientation of minerals. So minerals will take preferred orientation, in which the platy minerals, platy, that's elongated minerals, platy mineral grains exhibit parallel to subparallel alignments. So when you get alignments of the platy grains, elongated grains, that's foliation. So foliation describes any planar arrangement of mineral grains or structural features within a rock. So what the examples of foliation? Parallel alignment of platy or elongated minerals. Okay? And the same thing, parallel alignment of flattened mineral grains or pebbles. Okay? Or compositional banding of dark and light minerals, like the one we saw in the gneiss. And the other one, cleavage, where rocks can be easily split into slabs. So all of these features represent examples of foliation. Okay. So foliation can form in various ways, including rotation of platy crystals or minerals, recrystallization that produce new minerals perpendicular to the direction of maximum stress, flattening spherically shaped grains, okay? Development of foliation as a result of differential stress. So here we have igneous rock, and this is metamorphic rock. We have bands here. What was here? The crystals randomly arranged, but when we applied pressure, the crystals aligned. And this alignment gave me these bands, white, dark white bands. White one we said felsic mainly, felsic minerals, feldspar and silica, and the dark bands is their mafic minerals, magnesium and iron, dark ones. So this is what we call differential stress. Okay. And here we have solid state flow. These grains of sand, quartz grains, when pressure applied, what happened to this grain? For example, this grain starts slipping or having zones of slippage or fractures inside the crystals, and then the crystal rearrange it perpendicular to the stress, and the shape of the grain changed from circular to elongated or flattened. And this is rearrangement of the grains in a solid state. Okay, metamorphic textures. We have foliated and non-foliated. Foliated, slate, phyllite, examples. Low grade, Phyllite higher grade of metamorphism. Uh, sorry, Phyllite and schist intermediate, and then high grade is gneiss, the highest grade. Okay, what's slate? Slate looks like exactly like shale, parent rock, split into thin slabs. Description of this rock develops in bands of shale with low grade of metamorphism. Phyllite, it looks like the slate, but it's a glossy, shiny because it has very fine crystals. It gives the phyllite the glossy or shiny appearance. Schist, platy minerals. So minerals starts growing as elongated or rod-shaped minerals, and you can't see them with your naked eyes. So you don't need microscope to see the large elongated crystals, but in the phyllite you can't see the crystals with your naked eye. Most of the what happens in the schist, mica and chlorite flakes begin to recrystallize into larger muscovite and biotite crystals. Okay, exhibit a planar or layered structure, so it has layered structure. Rocks having this texture are referred as schist. Nice texture during high grade of metamorphism. Ion migration results in the segregation of minerals into light and dark bands. Light bands, feldspar and silica, or silicate, and dark bands, mafic, magnesium, and iron. Metamorphic rocks with this texture called gneiss. So gneiss texture, gneiss rocks. Although foliated, gneiss do not usually split as easy as slate and schist. Okay, now we'll go to non-foliated metamorphic rocks. Okay, well, what about them? Are composed of minerals that exhibit equidimensional crystals and lack of foliation. Develop in environments in which deformation is minimal. So stress is minimal, heat, mostly heat. Marble, quartzite, hornfels are the main examples. The parent rock of marble is limestone. Parent rock of quartzite is quartz and snow. Hornfels, parent rock of the hornfels, mostly shale. Now we have another type. We call it porphyroplastic texture. Usually large grains called porphyroplastis, crystals, large crystals, are surrounded by fine grain matrix of other minerals. We'll see example for this. So let's look at these. The classification of metamorphic rocks. Here, metamorphic texture, comments, and parent rock. Slate, low grade of metamorphism. Phyllite, and then schist, intermediate. Phyllite, schist, intermediate, and then gneiss. Slate, no banding, no foliation, no banding. But the only thing it has just the breakage perpendicular to the bedding plane. Parents is shale. Phyllite, parents still shale. It looks like slate, but it's a little bit shiny because it has very small crystals, microscopic crystals. As the grade of metamorphism increases, the crystals will grow and gives you the platy shape, and the texture will change into schist texture. And then we'll get to the higher grade of metamorphism. We call it gneiss, where we have bands of dark and light, very visible bands of dark and light minerals. Those are the foliated minerals. The non-foliated, marble, quartzite, hornfels. Marble, the parent of the marble dolomite. You see the crystals locked up, no space between crystals. Quartzite, coming from quartz, sandstone, parent. Hornfels, the parent, is mostly shale. Okay? And the comments here telling you as you go from shale, slate, to Nice, the crystals increase in size. This is slate. This is phyllite, shiny, glossy. Schist starts seeing larger crystals, but if you go, you can't see larger crystals. But here, the mica schist, there's schist made of mica, mostly the dark black one, black crystals. And then you get to the highest grade of metamorphism, nice, where you have bands, light and dark bands. Marble, no, all of these, oh sorry, let's go back. From slate, phyllite, schist, nice, all of these foliated. Now marble, non-foliated. It's coming from limestone, parent rock. Quartzite, this one quartzite here, and this is the original parent rock quartz, has crystals, but close-up view for the quartzite after metamorphism. No space between crystals, locked up and fused together. Here the porphyroblasts. So we have garnet crystals, these garnet crystals, floating on mica schist. This rock is a schist, metamorphic schist, made up of mica and has crystals of garnet. So that's what we call it, porphyroblasts. Okay. Common metamorphic rocks, foliated rocks and non-foliated rocks. Here, foliated rocks, slate, phyllite, schist, nice, going from low grade of metamorphism, intermediate to high grade of metamorphism. Slate, minute mica flakes. It has excellent rock cleavage and it's low grade of metamorphism. And then phyllite, very fine, it has very fine crystals of either muscovite or chlorite. And it's shiny and glossy, phyllite. Schist, 50% platinum, so elongated minerals, muscovite and biotite. Okay? And the parent material mostly shale, like phyllite and slate shale. Okay? And mostly it has chlorite schist and talc schist if it's coming from basaltic rocks. Okay. Nice. So we now have granular minerals. Minerals became grains, large minerals, and we have bands like light and dark bands. Segregation of light and dark silicate gives a nice characteristic foliated texture, which is the bands. Okay. The metamorphic rock sequence, which results from shale, are slate, phyllite, schist, nice. So low grade of metamorphism, slate, intermediate, low to intermediate phyllite, and then intermediate schist, and then nice, the highest. Okay, non-foliated rocks, marble and quartzite mainly. Marble was originally limestone. If it's dolomite, we call it wollastonite. The parent rock. Quartzite formed. It's also very hard metamorphic rock formed from quartz sandstone. And under moderate to high grade of metamorphism. And here's some comments. Pure quartz in white color. You see it in white color when you transform it to. If the quartz contains iron oxides, you see pink color, see it as pinky color, and contains dark minerals, you see it in gray color. Now the last one of the non-foliated hornfels. Parent rock is shale or clay-rich rocks. What about it? Baked by intruding magma bodies. So if the magma bodies intruded, the shale rock will produce the contact metamorphism or the contact zone between the magma and the rock and the parent rock, the shale parent rock. will form horn fells, which is completely baked. Occurrence of metamorphic rocks. Metamorphic rocks form in one of three environments: along fault zones, in contact with igneous bodies, during dynamic episodes associated with mountain building. So metamorphism along fault zones. So mainly we have here along fault zones stress, pressure, not temperature mainly, and friction heat produced along the fault zone. So mainly stress and friction heat. So and if we looked at the along the fault zones, there are two zones here, important zones. And the top part of the fault zones close to the surface will produce angular deformed metamorphic rocks. We call them breccia faults. At This is at the top, close to the surface of the along the fault zone. But if you go to the bottom of the fault zone, you will find the myelonite, which is another metamorphic rocks, but it went through ductile deformation. Breccia or fault of breccia went through brittle deformation. Contact metamorphism, when magma goes through or intrudes through sedimentary or igneous rocks, will form a contact zone between the magma and the sedimentary rocks, for example, and will form a halo or a zone of metamorphism. We call it halo or aureole. The size of the aureole produced is affected by, we'll see it in the figure, by the way. And this happened during contact metamorphism. The size of the aureole or the halo is affected by the size of intrusive magma body, this large magma or small magma, the mineral composition of the country rocks, the rocks that magma entered through, the availability of water. If there's more water, that zone will be bigger. If the magma is dry, that zone, the halo zone will be small. So hornfels, mainly metamorphic rocks produced by contact metamorphism. Regional metamorphism, rocks deformed by directional stress. Okay, and forms foliated metamorphic rocks. And this happens along the mountain building zones. And here there's a note: as we progress from areas of low grade of metamorphism to areas of high grade of metamorphism, changes in mineralogy and rock texture can be observed. True. So now let's go to metamorphic environments. We have contact or thermal metamorphism, hydrothermal metamorphism, burial metamorphism, subduction zone metamorphism, regional metamorphism, mountain building, metamorphism along fault zones, and impact metamorphism, which is meteorites. Contact or thermal metamorphism results from the rise in temperature during the invasion of magma to a host rock, sedimentary rock, or metamorphic rock. And it occurs where? In the upper crust, low pressure and high temperature. So contact thermal metamorphism, high temperature and low pressure. The zone of alteration, we call it halo or aureole, forms the rock in the rock surrounding the magma. Hydrothermal metamorphism. We have hydrothermal situation. The main metamorphic agent is the chemically active fluids caused by chemical alteration caused by hot iron-rich fluids circulating through the pore spaces in rock fractures. So contact or thermal metamorphism, the main agent, temperature. Hydrothermal metamorphism, the main agent, chemically hot fluids or chemically active hot fluids. Burial metamorphism, associated with very thick sedimentary strata in a subsiding zone, like Gulf Subduction zones. Metamorphism along subduction zones. Sediments on oceanic crust are subducted fast enough that pressure increases before temperature. So main one, or the main metamorphic agent is pressure here. Regional metamorphism produces the greatest quantity of metamorphic rocks associated with mountain building and the collision of continental blocks. Metamorphism along fault zones occurs at depth and high temperatures. Okay, high at depth and high temperatures. Pre-existing minerals deformed by ductile. So if I have rocks at the deeper part of the fault zone, will deform as ductile, will have a ductile deformation. But if there are rocks at the very top of the fault zone, close to the surface, that will be brittle deformation. If the deformation is ductile, the product, we call it myelonite, form in these regions of ductile deformation. Impact deformation occurs when meteorites strike Earth's surface. What's the product? Product of these impacts are fused fragmented rock plus glass-rich ejecta that resembles volcanic bombs called impactiles. So impactiles coming from impact metamorphism. Now let's look at the aureole. So we have magma body here, chamber, and we have host rocks, sedimentary rocks. So the magenta zone between the magma and sedimentary rocks, this metamorphic zone, we call it aureole. And after the igneous body or plutonic body crystallize it, we'll have crystallized plutonic body, metamorphic zone, and then sedimentary rocks. After these sedimentary rocks weathered, what's exposed on the surface? Aureole, metamorphic aureole or halo, and then under igneous plutonic body. Okay. Hydrothermal metamorphism, as we talked about, it has black smokers. So here we have magma coming from the bottom along the mid-oceanic ridges, and the ocean water, cold ocean water coming down. So there's circulation, cold, hot, cold. We'll have black smoky chimneys here, spewing hot mineral-rich seawater. This happens along mid-oceanic ridges, and here we can find metamorphic rocks like serpentinite and talc. Regional metamorphism. Here we have subduction zones, the pressure and heat. And that will lead eventually to the mountain building or the collision between the two continents. Metamorphism along fault zones. As we said, this is the fault zone here. The top part of the fault zone will have brittle fracture, brittle fracturing that will form breccia. So we'll see breccia here, fragments of the. But at the bottom of the fault zone, this is the top close surface, the bottom deeper, we'll find ductile flow, which is ductile deformation. And the rock will have different name, myelonite. So myelonite at depth and brittle ductile and breccia or gouge, it happens close to the surface. So this picture for the breccia, fault breccia, and this at the top close surface. This is for the myelonite at the bottom of the fault. So this is brittle deformation, and here for the myelonite is ductile deformation. Metamorphic zones, textural variation. Slate is associated with low degree of metamorphism. The opposite is gneiss, associated with high degree of metamorphism. What's in the middle, the intermediate, phyllite and schist. So if we're going through subduction zone, what we'll see here, away from the subduction, the high heat, pressure, and temperature, we'll see slate here, low degree. Then as you come closer, we'll find Phyllite. And then as we come closer, we'll find schist. And then as we come closer, we'll find gneiss. So as we come closer to the subduction zone, we'll find higher grade of metamorphism. So we can tell that we're headed to the zone of high heat and pressure as we follow the change in minerals and texture or foliation in the metamorphic rocks. Metamorphic zones, index minerals, and metamorphic grades. Changes in mineralogy occur from region of low-grade metamorphism to regions of high-grade metamorphism. Index minerals are good indicators of metamorphic environments. And here we have migmatites. Migmatites are rocks that have been partially melted, not completely melted. Represent the highest grade of metamorphism. And they are transition to igneous rocks. So let's look at the metamorphic zones and index minerals. Here we have parent rock, and here we have metamorphic rock. Parent rock is a shale, and low grade of metamorphism, intermediate, and then high. Low grade slate, phyllite, and then schist and gneiss. What minerals, what indicators? Index minerals, slate and phyllite. If we look here, we'll find dominated with chlorite, muscovite, and biotite, with quartz and feldspar, filling all these grades of metamorphism. And if we look at phyllite, we'll have more muscovite, more biotite, and less chlorite. If we look at the schist, we'll find storolites, garnet, a lot of garnet, more biotite, more muscovite, and less chlorite. As we go higher in the grade of metamorphism, we'll find sillimanite, just in the high grade of metamorphism. We'll find some garnet, some storolite, some biotite, but no muscovite, no chlorite, not dominant, I mean. And of course, still with quartz and feldspar. We can't find them in all these fields. And by this, we conclude the lecture of the metamorphic rocks, and we'll take a rest of 3 minutes to listen to the national anthem of Cyrenaica State, or Varga State.
فلك المراكز في الصدور يا أيها العالم النظير يحيى الأمين يحيى الأمين رفرف فأنت شعارنا وإلى الأمان منارنا بك علقت أبصارنا وإليك بالفخر نشير سجاف رابط واليوم قد آن المسير يحيى الأمير يحيى الأمير العلم نور حياتنا والدين خير هداتنا والصبر سور صفاتنا والله مولانا النصير يحيى الأمير يحيى الأمير.
Thank you very much.